Beneath layers of ice hiding two of the most intriguing worlds in our solar system lie vast, dark oceans teeming with mysteries just waiting to be uncovered. These hidden waters on Europa and Enceladus could hold clues to extraterrestrial life, challenging everything we thought we knew about habitability beyond Earth. Join me as we dive beneath the frozen surfaces to explore these alien underwater realms, where icy crusts conceal dynamic, possibly life-supporting oceans that might change our understanding of where life can exist. This journey into the unknown isn't just science fiction. It's the cutting edge of discovery that could reshape our perspective on the universe. Origins and formation of subice oceans. Beneath the icy crusts of Europa and Enceladus, worlds rekindled long ago in their formation, lie vast subsurface oceans that hold clues to planetary evolution and, potentially, extraterrestrial life. The origins of these hidden oceans trace back to the early processes of their parent moon's development, which involved a delicate interplay of heat, gravitational forces, and chemical composition. As these moons coalesced from circumplanetary disks, their internal heat was initially generated through accretion, collisions, and compaction of material, causing differentiation and melting in their interior layers. This heat, combined with the decay of radioactive elements, created a warm, semi-fluid environment beneath their icy surfaces. Over time, the internal heat diminished but persisted enough to keep water in a liquid state beneath the crust, especially when aided by tidal heating. Particularly for Europa, gravitational interactions with Jupiter and neighboring moons generate enough flexing of its interior to sustain a continuous supply of heat. Enceladus, orbiting Saturn, experiences similar tidal forces from its parent planet and nearby moons, which generate frictional heat deep within its icy shell. These gravitational stresses facilitate the maintenance of a liquid water layer beneath the ice, preventing it from freezing solid and maintaining a stable ocean for extended periods. Chemical processes also played a significant role in the formation of these subice oceans. During the early differentiation of each moon's interior, minerals and salts dissolved in the water, forming brines that lower freezing points. This composition increases the likelihood of liquid water existing at relatively low temperatures. Hydrothermal activity might have further contributed by injecting heat and minerals into the ocean from the moon's rocky core, creating a dynamic chemical environment that could support life. These processes create a self-sustaining system where heat and chemical energy perpetuate the stability of the subsurface ocean. The formation of these oceans is thus a complex story of initial accretion, radioactive decay, tidal flexing, and chemical evolution. Each moon's unique orbital dynamics and internal composition have shaped the scale, longevity, and chemical makeup of their hidden seas. Their existence today depends on a fine balance, a continuous supply of heat that prevents complete freezing, allowing them to persist across geological timescales. Exploring these origins reveals a portrait of planetary processes that parallel Earth's own history, yet unfold in extreme, remote environments that challenge our understanding of water's resilience in the cosmos. Characteristics and composition of Europa's ocean. Beneath Europa's icy shell lies a vast, concealed ocean that dwarfs all terrestrial bodies of water in volume. This ocean is believed to be a salty, high-pressure environment, with its capacity for holding more water than all the Earth's oceans combined. Its depth likely exceeds 10 kilometers in some regions, creating a mystical, layered world separated from the moon's surface by merely a few kilometers of ice that can be several kilometers thick itself. The composition of this ice-water interface varies, but scientists suspect that the vast majority of the ocean's composition is dominated by a salty brine, enriched with magnesium and sulfate minerals, which influence its physical dynamics and potential habitability. The chemical makeup of Europa's ocean appears to be shaped by interactions between the rocky core and the overlying water, a process known as ocean-planet interaction. Olivine-rich rocks within the silicate mantle might undergo hydrothermal alteration, releasing elements such as magnesium, sulfur, and potassium into the water. This process creates an environment surprisingly similar to Earth's deep-sea hydrothermal vents, rich in life-sustaining chemicals, but devoid of sunlight. The ocean's salinity is thought to be comparable to Earth's salty seas, although the exact concentration remains uncertain. Some models suggest the presence of sulfate and chloride ions dominate the water, which could influence the mineral deposits on Europa's ocean floor and any potential biosignatures. Heat sources beneath the ice maintain the liquid state of this hidden ocean. Tidal flexing caused by Jupiter's gravitational pull generates friction and energy within Europa, keeping water in a liquid form despite its extreme distance from the Sun. This continuous internal heating leads to the formation of a subsurface ocean that remains in a liquid state over geological timescales. As a result, the ocean is not just a static body of water, but likely a dynamic environment with convection currents, hydrothermal activity, and possibly even pockets of mineral-rich, mineral-laden water that slowly circulate near the rocky mantle. This circulation could allow nutrients and energy sources to reach the ocean's depths, providing conditions that could support life. Dots of evidence collected from spacecraft missions and spectroscopic data support the idea that Europa's ocean might harbor a complex chemical environment capable of supporting life. The presence of cracks and ridges on the icy surface suggests exchange processes between the ocean and surface ice, hinting at a lively and chemically active system. If life exists in Europa's ocean, it would most likely exploit chemical energy rather than sunlight, relying on processes similar to extremophiles found around Earth's deep-sea vents. The composition and characteristics of this underground ocean make it one of the most promising targets in the search for extraterrestrial life within our solar system, exciting scientists and astronomers constantly seeking more clues. Characteristics and composition of Enceladus's ocean. Enceladus boasts a subsurface ocean that is thought to be a tidally heated, salty, liquid water environment lying beneath an icy crust. This ocean is believed to be in contact with the Moon's rocky core, facilitating complex chemical interactions. One of the defining features of Enceladus's ocean is its salinity. Analysis of particles and water plumes detected by the Cassini spacecraft indicates high concentrations of sodium chloride, similar to Earth's seawater. The presence of these salts suggests that the ocean has been subjected to long-term aqueous processes, possibly leading to the concentration of minerals and nutrients critical for microbial life. The composition of Enceladus's ocean is not merely salty water. It contains a mixture of dissolved organic molecules, silicate minerals, and carbon dioxide. Organic compounds, some of which are complex, have been identified in the plumes ejected from the Moon's south pole. These molecules serve as potential building blocks for life, and their presence suggests that organic chemistry is ongoing beneath the icy shell. The ocean's acidity and pH levels are still subject to investigation, but models point toward a slightly alkaline environment, similar to Earth's oceans, which could promote chemical reactions favorable to life. Temperature conditions within the ocean are maintained by tidal heating, generated by gravitational interactions with Saturn and neighboring moons. This heating keeps the water in a liquid state despite the immense pressure from the overlying ice layers, which can be several kilometers thick. The temperature at the base of the ice shell might be close to freezing or slightly warmer, sustaining a delicate balance that supports a dynamic, potentially habitable environment. The conditions allow for convection currents within the ocean, which could facilitate the transport of nutrients from the rocky interior to the upper layers, creating a potentially nourishing environment. In essence, the characteristics of Enceladus's ocean, its salty, organic-rich composition, thermally maintained liquid state, and interaction with mineral-rich rocky layers, paint a picture of a complex, fluid world deep beneath the ice. These features make it a prime candidate for studying extraterrestrial habitability and understanding how life might exist in environments that are radically different from Earth's surface. The ongoing research continues to unravel the chemical intricacies of this subsurface ocean, offering tantalizing clues about its potential to host life beyond our planet. Implications for life and future exploration. The hidden oceans beneath the icy crusts of Europa and Enceladus represent some of the most promising frontiers in the search for extraterrestrial life. These subsurface seas are kept in a liquid state by the immense gravitational forces exerted by their parent planets, Jupiter and Saturn, generating tidal heating that prevents the water from freezing solid. In Europa's case, The ocean is believed to lie beneath a 15–20 kilometer thick ice shell, while Enceladus's ocean is relatively thinner but still potentially vast. The chemical interactions at the seafloor, where water meets rocky material, could create environments similar to Earth's deep-sea hydrothermal vents, fostering the conditions necessary for life to develop. The implications for potential life are profound. On Earth, ecosystems thrive in extreme environments devoid of sunlight. Think hydrothermal vents or subglacial lakes, relying instead on chemical energy from their surroundings. Enceladus and Europa's oceans may host similar ecosystems, sustained by hydrothermal activity at the ocean floor, releasing nutrients and energy needed for microbial life. Plumes erupted periodically from Enceladus's south pole, containing water vapor, organic molecules, and possibly even complex carbon-based compounds, suggest active processes at the ocean floor. These plumes offer scientists a rare opportunity to analyze subsurface ocean contents without drilling through thick ice, making their study more feasible. Future exploration could revolutionize our understanding of life's potential beyond Earth. Robotic missions, like NASA's upcoming Europa Clipper and ESA's JUICE spacecraft, aim to analyze the composition of surface materials and plumes. Close-up analysis of sea salts, organic molecules, and minerals could indicate biological or prebiotic activity. Advances in autonomous submersibles or ice-penetrating probes could eventually allow direct sampling of the ocean itself, reaching environments that might harbor microbial communities. These efforts will require overcoming immense technical challenges with drilling through kilometers of ice and operating in extreme cold and pressure conditions, but could open doors to discovering extraterrestrial life forms or conditions conducive to life's emergence. This exploration might also refine our understanding of the conditions that support life in the universe, shaping theories about habitability on other celestial bodies. The oceans of Europa and Enceladus could be considered cosmic laboratories, illustrating how liquid water, chemical energy, and a stable environment, hidden beneath thick ice, are enough to sustain life. As research progresses, we might find that the existence of such environments is more common than previously assumed, influencing future searches for life on Europa, Enceladus, and beyond. The potential discovery of life there wouldn't just answer scientific questions, it would redefine our place in the cosmos, sparking new philosophical and existential debates about the universality of life. Usnovnoy, Rusgil 5. Beneath the icy surfaces of Europa and Enceladus lies a hidden world that excites scientists and explorers alike. These subsurface oceans are believed to contain more water than all of Earth's freshwater reserves combined, held beneath thick layers of ice that can be kilometers thick. In Europa's case, the ice shell is estimated to be between 15 to 25 kilometers thick, concealing an ocean that may lie over 100 kilometers deep. Similarly, Enceladus hosts a smaller but highly intriguing subsurface ocean, hidden beneath a crust just a few kilometers thick in some regions, with evidence of cryovolcanic activity that suggests ongoing exchange between the ocean and space. These environments are thought to maintain conditions that could potentially support life, making them prime targets for astrobiological research. The most compelling evidence for these underground seas comes from a combination of satellite imaging, gravitational measurements, and surface geology. In Europa, giant fractures across the ice shell, known as lineae, indicate that the ice is constantly stretching and cracking, likely due to the ocean's movement beneath. The presence of salty, mineral-rich water has been inferred from magnetic field data collected by spacecraft, showing that the liquid layer is a highly conductive salty brine. For Enceladus, the Cassini mission detected plumes of water vapor erupting from cracks in the moon's south pole, dubbed tiger stripes. These jets contain organic compounds and water vapor, suggesting a dynamic, active ocean beneath, possibly interacting with mineral-rich rocky seafloors. Understanding the composition and dynamics of these hidden seas is vital for assessing their habitability. In Europa's ocean, hydrothermal vents on the ocean floor could provide energy sources for microbial life, similar to those found around Earth's deep-sea vents. The salinity, temperature, and mineral content of these waters are critical factors. They influence whether life could exist and in what forms. Enceladus's ocean, with its geochemical analysis of plumes, has revealed complex organic molecules, fueling hypotheses that it might host environments suitable for simple life forms. The challenge lies in studying these oceans directly, as reaching below the ice layers requires technological advancements in drilling or submersible probes, which are currently being developed for future missions. The importance of these subsurface oceans extends beyond scientific curiosity. They push the boundaries of what we consider habitable environments and broaden the scope of our search for extraterrestrial life. If life exists on Europa or Enceladus, it would suggest that habitable conditions might be widespread throughout the universe, not limited to Earth-like planets within the habitable zone. Future missions, such as the European Space Agency's Jupiter Icy Moons Explorer, JUICE, and NASA's Dragonfly, aim to explore these worlds more closely, searching for signs of biological activity and understanding the geophysical processes maintaining these submerged oceans. The unseen depths beneath thick ice sheets hold more mysteries than one could imagine, promising discoveries that could redefine our understanding of life's potential beyond Earth. As we wrap up our journey beneath the ice of Europa and Enceladus, it's clear that these hidden oceans are among the most intriguing frontiers in our quest to understand the cosmos. Their vast, alien waters may hold clues about the potential for life beyond Earth, fueled by the interactions between liquid water, heat, and the rocky interiors. We've seen how scientists are piecing together these icy mysteries through robotic missions, spectral analysis, and innovative exploration techniques. Thinking about the possibility of microbial life thriving beneath miles of ice is both humbling and inspiring. It reminds us that curiosity drives human progress, and there's still so much to discover just beneath the surface of these frozen worlds. If this glimpse into the subsurface oceans sparked your interest, stay tuned. Future missions and breakthroughs are on their way, promising to unlock even more secrets about what lies beneath the ice. Thanks for coming along on this adventure. There's plenty more to explore, and first can't wait to share what we'll find next. Until then, keep pondering the depths. The universe's hidden worlds are waiting.